Some images have the power to change the world. You might remember that iconic photograph, Earth seen from the moon, captured by Apollo astronauts. A simple blue marble, suspended in the void, fragile and alone. But today, I want to tell you about a different image. An image that forever changed how I see the world, the universe, and our place in it. An image that gave me a feeling so strange, so profound, that it haunts me to this day. Are you ready? Here it is. At first glance, it looks like a simple photo of the sky, just some dots and smudges against darkness. But I am about to show you why this photograph is far more important than anything you could have imagined. This image comes from the James Webb Space Telescope. It shows a tiny fragment of the sky, so small that if you held a pinhead at arm's length, that is the portion of sky you would be covering. But in this seemingly empty space, we do not just find a few stars. We find thousands of galaxies, each one like our own. Milky Way, containing billions of stars and probably just as many planets. And that is just the beginning. This image revealed galaxies so distant, so faint, that they were invisible to previous telescopes, even Hubble. Some of these galaxies emitted their light more than 13 billion years ago, when the universe was just a child. In a single photograph, we have essentially traveled back in time, further than ever before. But here is what is even more fascinating. This image was not taken of some special region of the sky. It was taken of a completely ordinary area, chosen precisely because it appeared empty. And yet, it is overflowing with galaxies. So imagine if a fragment this small is this rich with galaxies. What about the rest? The more we look, the more we discover. Galaxies upon galaxies, stretching further and further. Each step reveals new secrets, as if the universe has no end. And that is when a question started to haunt me. A question that consumed me for days, for weeks. How far does it go? Is the universe infinite? Does it have a limit, a boundary, something beyond which there is nothing more, no more stars, no more galaxies? At the edge of the universe, is there a wall, an impenetrable barrier, or does it just keep going forever? But rather than drown you in equations and abstract theories, today I propose something simpler. What if we just went there? Today, I'm taking you on a journey. You and me, inside a fictional spacecraft, heading toward infinity. Together, we will discover what lies at the very edge of our universe. Let's go. We feel a deep rumble, then an incredible thrust as our rocket launches toward the sky. We've just left Earth's surface, our cradle. Within minutes, the atmosphere thins, the sky darkens, and thanks to advanced technology, we reach low Earth orbit. A seemingly impressive feat, but in reality, barely a first step. Below us is the International Space Station, orbiting just 400 kilometers above the ground. That's barely the distance from Los Angeles to San Francisco. Yet even at this trivial altitude on a cosmic scale, the landscape transforms. We can clearly see Earth's curvature, the thin blue layer of our atmosphere, and above all, the eerie silence of space. But we've barely gone anywhere. The moon is nearly 400,000 kilometers away, 1,000 times farther than the International Space Station. Even the most powerful rockets in history, like Saturn V, took 3 full days to reach it, and that's nothing compared to interplanetary distances. The Sun, our star, is 150 million kilometers away. Light, the fastest thing in existence, takes over 8 minutes to reach us. 8 little minutes for a photon to leave the Sun's surface and strike our retina. Yet that's already an eternity for human space travel. Mercury, Venus, Mars, each orbit the Sun at distances of tens or hundreds of millions of kilometers. Compared to these numbers, the International Space Station altitude, or even the distance between Earth and the Moon, are laughably small. As we travel farther from Earth, farther from lunar orbit, we realize that what we call the solar system is actually a vast black desert, where planets and asteroids are tiny oases lost in silent immensity. First, there's the inner solar system, the region containing the four rocky planets, Mercury, Venus, Earth, and Mars. In ancient times, people didn't know these were rocky worlds. They saw wandering points of light they called planets and attributed divine powers to them. Mercury, small, fast, and close to the sun, bears the name of the swift messenger of the Roman gods. Venus, goddess of love and beauty, is associated with that brilliant morning and evening star, eternally closer to the sun, brighter than all other planets. Today we know Venus is a suffocating hell. Mars, god of war, appears red to the naked eye. The ancients saw it as a symbol of blood and conflict. But the reality is more subtle. It's the oxidized surface that gives this rusty color. Mars is red because it's literally rusted. On the scale of our journey, Mars is already much farther than the Moon, but it's still a neighboring world. Leaving the inner planets, our spacecraft crosses the asteroid belt, a vast ring of rocky debris. You might expect a dense field of tumbling rocks, but it's quite the opposite. Even here, the average distance between large asteroids is measured in millions of kilometers. Our vessel flies through this silence, occasionally passing a rock or chunk. Ceres, the largest, is barely a drop of water in an ocean of emptiness. Beyond that, we enter the realm of the gas giants. Jupiter, king of the gods and the most massive, sits over 5 astronomical units from the Sun. Each astronomical unit equals 150 million kilometers. Light takes over 40 minutes to travel this distance. For an Earth probe, that's already years of navigation. The farther we go, the more abstract the distances become. Uranus and Neptune, dozens of astronomical units away, are nothing but bluish, icy specks, battered by unimaginable winds. Voyager, launched in the 1970s, took a decade to reach these outer regions. Beyond Neptune extends the Kuiper Belt, a field of icy objects, among which Pluto, once considered a planet, is just one member among many. New Horizons, one of our fastest probes, took nearly 10 years to get there. And yet, that's not even the end. Far beyond, at thousands and tens of thousands of astronomical units, lies the Oort cloud, a sort of reservoir of comets. It could extend up to nearly 2 light years, a quarter of the distance to the nearest star. Even accelerating constantly, the notions of time and distance blur. Numbers stretch, become incomprehensible. If the solar system already seems like a bottomless pit, what about the spaces between the stars? The cosmos is a black desert, dotted with a few shining pearls. At this point, the mind reels. Where we are now, all those beauties are tiny points lost in the distance. Our vessel speeds on, and the solar system we thought was immense is just the first step of an endless cosmic staircase. It's time to push even further. We're now entering interstellar space, a void even more immense, where the solar wind fades, where the sun's direct influence diminishes, and where its gravity gradually yields to that of other stars in the galaxy. Here, every direction looks the same. No north, no south, no obvious landmarks. The very concept of neighborhood takes on a dizzying dimension. The void feels endless, and the neighborhood is no longer what we expect. The closest star to the Sun is Proxima Centauri, located about 4.24 light-years away. 1 light-year is the distance light travels in a year, roughly 10 trillion kilometers. On our scale, it is inconceivable. Our spacecraft, still accelerating, must multiply its speed by tens, hundreds, perhaps thousands for this distance to become manageable in reasonable time. And even then, it would remain a colossal journey. Proxima Centauri is a modest red dwarf, invisible to the naked eye from Earth. It orbits near the Alpha Centauri system, a set of bright stars that, seen from the southern hemisphere, form a familiar marker in the sky. Proxima hosts an exoplanet, Proxima b, located in the star's habitable zone, meaning the right distance for liquid water to be possible on its surface. Yet we know almost nothing about this world. Is it rocky? Does it have an atmosphere? Water? This planet is, on a cosmic scale, right next door to us. And yet it remains a mystery, perched at the bottom of the night. If we continue, we'll enter a radius of a few dozen light years around the Sun. Within this restricted bubble, there are approximately 1,400 solar systems, and more than 2,000 stars if you count multiple star systems. A true cosmic crowd, but a crowd invisible to the naked eye. So enormous are the distances. This bubble is both crowded and eerily empty. Among these thousands of stars, most are red dwarfs, faint and cool, shining with a pale glow, living for billions of years. There are also more massive stars, yellow dwarfs similar to the Sun, cooler orange dwarfs, red giants at the end of their lives, or a few rare, extremely luminous blue stars, heated to such high temperatures that they dazzle their surroundings. And then there are the exoplanets. Since the 1990s, we've known that exoplanets are not unique to the Sun. Astronomers have detected thousands of exoplanets, and most nearby systems harbor at least one. Some are in their star's habitable zone, making us dream about the existence of liquid water. Others are scorching gas giants, orbiting so close to their star that their year lasts just a few days. Still others are super-Earths, more massive than Earth, but smaller than Neptune, with conditions ranging from paradisical to hellish. Take, for example, the star Ross 128, about 11 light-years away. This modest red dwarf hosts a planet, Ross 128b, whose surface conditions could be surprisingly close to Earth's. Its mass is slightly greater than ours, gravity barely stronger. Temperature could be just a few degrees below Earth's average. It's a potentially temperate world, maybe even a haven, but it is so far away. Even at the speed of light, it would take us more than a decade to get there. At 16.8 light-years, we could pass Altair, a blue-white star, brighter, more massive, and hotter than our Sun. Altair spins so fast on its axis that it is flattened. Farther still, at 25 light-years, we could approach Fomalhaut, a triple star system with a bright, young yellow star. It is surrounded by a protoplanetary disk of gas and dust, a true cradle for future worlds. However, stars are not eternal. They are born, they grow, they consume their nuclear fuel, sometimes spawn planets, and eventually die, leaving behind white dwarfs, neutron stars, or sometimes black holes. We could spend hours, days, years discussing each neighbor, each peculiarity, each strange exoplanet. Some worlds might be gigantic oceans with no solid surface. Others might be icy deserts or volcanic furnaces. The scale swallows our intuition, and only time and patience reveal the true variety of the cosmos. The distances are so vast that our knowledge remains fragmentary. It is based on a few measurements of stellar radiation, on the gravitational wobble of stars, and on the faint planetary glimmers that pass in front of their suns. As we continue moving away from nearby stars, we enter another dimension of immensity, that of the galaxy itself. The Milky Way, our cosmic home. We have just left a bubble of about 50 light-years, already filled with thousands of stars. But that was just a drop in an ocean. The Milky Way is about 100,000 light-years across, a spiral disk containing several 100 billion stars. The Sun, on our scale, is just an unremarkable point located about 25,000 light-years from the galactic center, nestled in a secondary spiral arm called the Orion Arm. Most of the stars we see at night, or detect with our telescopes, lie within a radius of a few hundred, maybe a few thousand light years. A trivial volume compared to the galaxy's total size. Try to imagine the scale. If the sun were reduced to the size of a blood cell, then the Milky Way would be as large as a continent, like a Europe 3,000 kilometers wide. Continent. The spaces between stars are mind-boggling. What we previously considered immense interstellar gulfs were in fact just small gaps. Here, we are talking about crossing not just a few light years, but a few thousand, then tens of thousands, just to traverse a single arm of the galaxy. We would have to imagine immense time frames at incredibly high speeds. At the center of the galaxy lies a fascinating object, a supermassive black hole named Sagittarius A star. Its mass is estimated at about 4 million times that of the Sun. Supermassive. Around it is a gigantic bulge of ancient stars, packed into a region where stellar density is much higher. Gigantic bulge. From there emerge the spiral arms, rich in gas, dust, and star-forming regions. Nebulae are examples of these stellar nurseries, bubbles of gas and dust giving birth to new generations of stars and planets. Now our spacecraft continues accelerating. Even if we could travel at a significant fraction of the speed of light, crossing the galaxy would remain a titanic task. At the speed of Voyager 1, which travels at about 17 kilometers per second, it would take 550 million years to reach our destination. Million years. As we leave the Milky Way, our spacecraft penetrates territory, where distances are no longer measured in thousands of light years, but in millions. The local group, a collection of about 50 galaxies, dominated by 3 spiral galaxies, the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy, spans about 10 million light years. Around these giants orbit dwarf and irregular galaxies, sometimes barely larger than a star cluster. The Milky Way, however gigantic, is just one island among many in a galactic archipelago. Andromeda, located about 2.5 million light years away, is the nearest large spiral galaxy. It is thought to contain up to 5 times more stars than the Milky Way, and a complex core suggests it has already swallowed other galaxies in the past. Our vessel, still accelerating, crosses intergalactic space. The galaxies of the local group are not randomly distributed. They interact gravitationally. The future collision between the Milky Way and Andromeda in about 5 billion years will be of a scale that is difficult to imagine. 2 gigantic spiral galaxies will merge to form an even larger elliptical galaxy. But for us, these billions of years are almost abstract. We cross in moments regions that even photons take millions of years to traverse. If we expand our field of view even more, the local group appears as a small entity within a much vast structure, the local sheet, then the Virgo supercluster. These galaxies are not simply scattered randomly. On a large scale, they gather into filaments, clusters, and superclusters, forming a cosmic structure resembling a gigantic spiderweb. The Virgo supercluster, to which we belong, extends over more than 150 million light years. It contains thousands of galaxies distributed in clusters and groups. At our speed, relativistic effects begin to make themselves felt. Past, present, and future become almost abstract concepts, distorted by the rapidity of our movement. Space itself contracts in the direction of our motion, making what is theoretically inaccessible much less distant. But this relativity is not enough to cancel out the enormity of distances. And that is not all. At these scales, the expansion of the universe comes into play. Beyond a few 100 million light years, galaxies move away from each other like points drawn on a balloon being inflated. This is cosmic expansion. The farther we look, the faster distances increase. This expansion, which we have barely mentioned, will become critical for understanding the ultimate limits of our journey. But for now, let us just remember that at the scale of superclusters, gravity is not enough to hold galaxies together. Entire portions of the universe are drifting apart, and some objects, however luminous, might never be accessible because their light could never reach us. Thus, at the scale of the local group and superclusters, we realize that our galaxy is just one brick in a wall of galaxies, itself microscopic compared to the entire universe. Even with our spacecraft, with its limitless acceleration, we are only diving deeper and deeper into a bottomless abyss. Taking a step back, we see that the universe resembles a gigantic labyrinth, where each level of structure contains a more vast one. We've now reached the ultimate limits of our cosmic expansion, where light itself is no longer enough to illuminate distant abysses. Until now, we've crossed the solar system, the stellar neighborhood, the galaxy, the local group, then the galaxy superclusters, noting at each stage that the universe is vaster than anything we could have imagined. Yet even after crossing hundreds of millions and then billions of light years, we have not found an edge, no solid wall, no sign that says end of universe. We are facing a more subtle horizon, the cosmological horizon. The cosmological horizon is the limit beyond which light has not had time since the Big Bang to reach us. To understand this, we must remember that the universe has a finite age, about 13.8 billion years. Light travels at a constant speed, so there exists a region beyond which no photon has been able to reach us. This wall is not a material barrier. It is an effect of time and the finite speed of light. From Earth, the observable universe forms a sphere 93 billion light years in diameter. That is much larger than 13 billion light years because the universe has expanded since the light we now see began traveling. Thus, regions once closer have moved away. But there is an even more extreme concept, the Hubble wall, or Hubble sphere. This is the distance from which the expansion of the universe makes objects recede faster than light. Not because these objects move locally faster than light, but because it is space itself that is stretching. So beyond a certain distance, light emitted today will never be able to reach us because space is stretching faster than the light can progress. We are touching here on the true dynamic nature of the cosmos. The expansive nature of the universe and the existence of the cosmological horizon cannot be overcome. Certain regions of the universe are and will remain inaccessible to us. And this is where questions of theoretical physics about the shape, the size, and the geometry of the universe come into play. What shape does the universe have beyond? Is the universe flat, open, or closed? The answer depends on the total amount of matter and energy it contains, and on a key threshold called critical density. Critical density is a theoretical equilibrium point that determines the curvature of space itself. If the total density of matter and energy matches this level exactly, the universe adopts a so-called flat geometry. In such a cosmos, the familiar rules of Euclidean geometry apply. Parallel lines do not meet, and the sum of the angles in a triangle remains strictly 180 degrees. Space could then extend infinitely, without ever closing in on itself. If the density exceeds the critical value, things take a different turn. Space acquires positive curvature, like the surface of a sphere, except here it is a four-dimensional structure that folds in on itself. In a so-called closed universe, we could travel in a straight line, again and again, and end up back at our starting point. It is a bit like going around Earth, but with an extra dimension. The universe would have no edge per se, yet it would be finite and contained within itself. Conversely, if the universe's density proves lower than the critical density, the curvature becomes negative, recalling the shape of a horse saddle. Trajectories behave strangely. Parallel lines would move away from each other endlessly, and the universe would extend without end, potentially infinite as well, but very different from a flat space. This open geometry suggests a cosmos where distance and direction blur, and our notions of what is straight or curved transform. Actual cosmological data, notably from the cosmic microwave background, suggests that the universe is extremely close to flat, within a tiny margin of error. That means that within the limits of our observations, the universe appears almost perfectly flat. If it is perfectly flat, it could be truly infinite. If it is nearly flat, it could nevertheless be immensely large, with a horizon hundreds or even thousands of times larger than the horizon of the observable universe. In other words, even the most optimistic scenarios suggest the universe far exceeds everything we can see. What we call the observable universe is just a tiny piece of a much vaster whole. This conclusion has dizzying implications. Even a spacecraft capable of accelerating endlessly could never probe the totality of the universe. At best, we could explore an increasingly large fraction of the observable universe. But the rest, beyond the cosmological horizon, will remain forever hidden. And if the universe is truly infinite, then no journey and no technology will allow us to traverse it entirely. Even the minimum size of the universe, established by cosmological measurements, guarantees that it is already far too large for us to ever hope to go around it. Science can only provide estimates, not absolute certainty. It gives us bounds and constraints. Beyond those bounds, the laws of physics, the speed of light, and the ongoing expansion of space decree that we can no longer observe anything, and that we may never know what lies beyond. So unfortunately, there is no easy answer. We do not know if the universe is infinite, nor where its limits are, if indeed they exist. And yet, it is precisely this uncertainty that overwhelms me. Even with a vessel of inexhaustible energy, accelerating indefinitely and having unlimited time, we could never explore more than a derisory fraction of the cosmos. We will never reach an edge, a final wall, an end to our epic. And that is the feeling this image, the one that started everything in me, gives me. This photo, by revealing a profusion of galaxies invisible to the naked eye, reminds me just how immense our universe is, beyond reason, beyond numbers, beyond anything our minds can conceive. At the heart of this infinite ocean, our Earth appears nothing more than a tiny oasis, a small island of complexity and life in a dark and silent desert.